This is a relatively short video on implicit differentiation. You saw implicit differentiation already in Calculus 1, but now that we have seen the chain rule in multiple dimensions, we can express implicit differentiation in a much more general way that, that makes a little bit more sense. It's a little bit more rigorous. So we go back to the problem of implicit differentiation, that instead of a single function, instead of supposing, say, z equals a function of f of x and y, we simply have a relationship among all three variables, x, y, and z, which is set equal to some constant, typically 0, because a non-zero constant could be included in the function f. So this is an implicit relationship between the variables x, y, and z. It's not explicit in the sense that any one of them is defined in terms of the others, but the three of them together are defined in this way by the function capital F. Now, this is one equation among the three unknowns, x, y, and z. So it places one constraint in 3 dimensions, gives us a 2-dimensional object. We should expect this function here to give us a 2-dimensional object. And if that 2-dimensional object is a surface, which it should be, then we can imagine calculating partial derivatives, rates of change of z with respect to x or y, or in fact, rates of change of either of the variables with respect to any of the others. So the way that we calculate those derivatives is to assume that despite the fact that there is no explicit global definition of z in terms of x and y, assume that locally in the vicinity of some point of interest, we can in fact express them as an explicit dependence. That as long as I don't consider too much of the surface, it is a single valued function of x and y. And so we can write this down. Assume that locally z is a function of x and y. And there's something called the implicit function theorem that tells us when that is okay to do. We'll actually see the answer later on as we proceed with this calculation. But for now, let's just assume this is okay. So how do we calculate partial derivatives with respect to, suppose, say, x? We take simply this original implicit description of the relationship between the variables. We take this equation and we differentiate both sides with x. That's all we're doing here. That is the key step in this process. Everything else is just using things that you've already seen. So what do we actually have to do when we take the derivative with respect to x of this left-hand side? Of course, on the right-hand side, we'll get 0. But on the left-hand side, we have a function of multiple variables. And so we need to use partial derivatives. And here, in fact, z is then now a function of x and y, and so we'll need the chain rule. So to do this, we have the partial derivative of f with respect to x. And to use the chain rule, then we take the derivative of the inside with respect to x. But here, that's just x. So it's partial f, partial x, partial x, partial x. And of course, that's just going to be 1. But then the more interesting thing happens. We take partial f, partial y, partial x, and that vanishes because y and x are independent variables in our way of thinking about the problem. Since we're trying to find derivatives of z with respect to x and y, we're thinking of x and y as independent variables, and so they don't depend on each other. So that partial derivative vanishes. And finally, our real application of the chain rule, partial f, partial z, but z itself depends on x and y, and so we need to take partial z, partial x. That gives us 0 on the right-hand side. Now, it's not obvious this was going to give us what we wanted, but it is clear that we can take the x partial derivative of both sides. And it turns out, since this term here is 1, that here now is the very term that we wanted, partial z, partial x. And so we can solve for partial z, partial x by simple algebra, and we get negative partial f, partial x over partial f, partial z. We're not actually doing anything like canceling the partial f's. You would see that if you think about these like fractions, canceling the partial f's would actually give you the wrong answer. It would say that partial z, partial x is negative partial z over partial x. So that doesn't make any sense. Do not think of this as canceling terms in a fraction. Instead, remember this key step. We just differentiated the whole implicit equation here with respect to the variable, the derivative that we were seeking. And then we solved for the resulting object we wanted to find, partial z, partial x. We see that this will work as long as partial f, partial z is not equal to 0. Okay, and so I told you earlier the implicit function theorem says when it's okay to treat this locally as an explicit function, and this is the condition, that partial f, partial z is not equal to 0. We'll see in a minute what interpretation that has. Similarly, suppose I want partial z, partial y. Following from the previous example, I might consider just taking the partial y derivative of the whole implicit equation, which we do right here. That gives us, when we use the chain rule, the x derivative vanishes, partial f, partial x, partial y vanishes because x and y are independent variables, don't depend on each other. Partial f, partial y, partial y, partial y, again, that will be 1. And partial f, partial z, partial y. Then we can solve for partial z, partial y, and we get a very similar expression here involving a fraction of partial derivatives of f. Again, we see that we can do this provided the partial derivative of f with respect to z is not equal to 0. So the pattern is that we can treat one of the variables as an explicit function of the others as long as the partial derivative of f with respect to that variable is not 0. So here we wanted to treat z as a function of x and y, and we can do that as long as the partial derivative of f with respect to z is not equal to 0. Please do not remember these formulas, just remember how it was done. It is a waste of brain space to remember these formulas. If you know you want to take implicitly derivatives with respect to y, just take the derivative with respect to y, and then you'll be able to solve for the derivative that you are seeking. So remember these two key steps, not this formula. This formula is too easy to misremember. And one example is all for this video. This is the equation for a sphere, x squared plus y squared plus z squared equals 2. And we're being asked to compute two partial derivatives, dz dx and dz dy at the point 1, 0, 1. X equals 1, y equals 0, z equals 1. We'll compute those partial derivatives, and then we'll see if that answer makes sense by comparing it to a graph of a sphere. So, since we're computing partial derivatives of z, we assume that in the vicinity of this point 1, 0, 1, that z can be written explicitly as a function of x and y. And now, to calculate dz dx, we take the x derivative of the whole implicit equation. I see I made a mistake. These should be 2's here. But nevertheless, it won't change the answer. When we take the partial x derivative here, we get 2x. This will go to 0. And here we will get 2z, and then by the chain rule, a dz dx. And so we simply solve for dz dx, and we get minus x over z. X is 1, z is 1, and so dz dx is minus 1. You can see that in practice, it's even simpler than the generic formulas that we had on the previous page. You just write down the equation, and you take partial derivatives, being sure to use the chain rule if one of the variables is assumed to be dependent on the others. Similarly for y, partial derivative with respect to y of the whole equation, we get 2y plus 2z, partial y, using the chain rule. And then we solve for dz dy, negative y over z. Here, y is 0, and so we get 0. Now, does this make sense? Does this line up with what we know about a sphere? We can go ahead and plot a sphere. This is the top of a sphere. And I've drawn it not quite correctly because 1, 0, 1 would actually be closer to here. It's not right at the edge because the radius of this sphere is the square root of 2. So this would be some point on the inside. But we can sort of see this is the x-axis in this direction. And so as x increases, we can see that this is rolling down the face of the sphere, and so z is decreasing. So we get a negative sign that makes sense. And here on the very side of the sphere, as y increases, we're just kind of walking laterally along the side of the sphere at this point. And so there's no change in y, so that does make sense as well. This is, of course, not necessary for actually computing the derivatives, but if you can visualize these things, it's a good way to check. Now, earlier we saw that we could assume that z was locally an explicit function of x and y, as long as partial f, partial z did not equal 0. So what happens if that equals 0? Now obviously you can't do that because you're dividing by 0, but what's happening on, say, this graph that would give us an interpretation of why that doesn't work out? Here, if df dz is 0, well, df dz is just going to be 2z here. And so if that's 0, that means z is 0. The only way df dz can be 0 is if z is 0. And what's happening when z is 0? Well, that's right down here at the bottom where this hemisphere touches the xy plane. And we know that at the edge of a sphere where it intersects the xy plane, in fact, the surface is vertical. So at all these points in the tangent plane where df dz is 0, the tangent plane is vertical. And so that's why we can't take local surfaces at such a point, because the surface would not be well defined, it would be vertical. So that's a physical interpretation of why you can only do this if the partial derivative with respect to z is not equal to 0. And I think that's all.